So maybe you all have this idea that a multi-layer perceptron is something that looks like this. So mostly you have different layers that are connected together and that try and find some sort of pattern at each stage of the neural net so as to use this information to classify or regress some quantity of interest. So I'll just won't go over all the text, and I'll jump directly to this part where essentially, so we're presenting these models because they are just a natural extension of what Bertrand was presenting before. So for those of you who have more of a computational background, actually the last layer of a multi-layer perceptron can be seen as something that's very comparable to logistic regression. So actually, what the model that logistic regression is using to predict a variable y is exactly what happens in the last layer of a multi-layer perceptron. Namely, you're doing a linear combination of the features of the layer just before, all right? So that would be x, and basically you do a linear mixture of that, and you pass it through a sigmoid, so a non-linear function that basically yields a function similar to what you see in this image. And this image is taken from Jérôme's presentation this morning. And in the end, so this is just a model, and basically for when you're training a multi-layer perceptron, you also need a loss, and it just happens that the loss that you're minimizing in the case of a classical multi-layer perceptron, one-layer perceptron in this case, is the exact same objective function to that of a classical logistic regression problem. So I don't want to go too much into the details, but the intuition, the motivation behind using multiple layer perceptrons is that maybe using linear mixtures of features is not enough to predict the variable of interest or the class of interest, and maybe combining these in a non-linear fashion could be interesting. And so essentially what you do when you have multiple layers in a perceptron is you try and hope that during the training phase, you will learn some non-linear combination of your features that will be interesting or like meaningful in your classification or regression task. All right, so I'll jump right into the notebook. So if you have downloaded, cloned the repo before and set up the environment, you should just run Jupyter Notebook. This hopefully will start not a kernel, but like you can start a kernel going to content and just clicking on MLP_decoding.markdown. This is the file that we'll be using here. And so essentially what happens in there is very similar to what Bertrand was showing you before. So we'll just go through the notebook. It's nothing new if you were here before. So we mostly use fMRI data collected in different subjects so as to train a decoder that tries and predict what the person is seeing. All right, so this first cell simply loads the data. This is the exact same cell that was used in the previous notebook, so no one should be lost at this stage. We went over the categories also that we can try and classify. This was done in the previous presentation, so I'll just be very quick here. There are, I think, 8 categories. We have a bit more than 1,000 samples on which we can try and train our decoder. And yeah, that's it. Right, so one of the first things we do is we need to tweak a bit the shape of Y. So what we use here is what we called a one-hot encoder. So instead of storing the index like the number of the category that we're trying to predict, we will store vectors such as this one. So, and this is what we'd like the MLP model that we'll be training in a few cells to output. Like, so we'd like them to make a prediction on what they think the category of this specific sample is. So in this line, what you see is that every category is set to 0. So because they're not the true category, and one of these categories, category number 5, is set to 1 because this is the true label. All right. And so you can see that the first few samples belong to category number 5. The few next ones belong to category number 3. All right. And so essentially, our MLP model should output something of the same shape. And if they are like super sure that category 5 is what they want to predict, then they should go all in on category 5 and have zeros everywhere and a 1 in category 5. But if they're hesitant in between two categories, this should somewhat reflect in the output of the model. All right. So same as before, really, we split the data into training data and test data, and then this is where we start actually building our multi-layer perceptron model. But first, we initiate the model as a keras object that is an instance of an object called sequential. So sequential is just an easy way to describe a series of layers. So mainly what you do is you describe what every layer should look like. So in terms of size, in terms of activation functions, etc. And so the first thing we do, so we add one first layer. Basically, what we say is we give it the number of features that we have in our data set. So here, remember that this number is it corresponds to the number of vertices or voxels that are present in the mask that we use at this moment. So this is basically akin to the number of pixels in the visual cortex that we're interested in this decoder. And then we shrink the dimension of this input to 50 dimensions. So and this is what we call a dense layer. So everything is connected together, and basically we'll try to learn weights that map features of our images, and that shrinks them to this dimension. We also have set the activation function to ReLU. So activation functions in this case are here. They serve many purposes, but the main purpose here is to introduce non-linearities. So ReLU is a function that looks like this. It basically is 0 for negative values, identity for positive values, and it enables you to introduce non-linearities across your different layers. All right. And you see, it's very using keras, but also other libraries. It's once you have a sequential object like this one, it's very easy to add a layer. So you just have this very cute API endpoint called add. All right, so that's it for the first layer. We can add another one and see for this layer, keras automatically understands what will be the input dimension. All right, so see, we don't have to here we don't have to say input dim equals 50. The API will just take care of that for you. All right, we use the same activation function, and finally we add another dense layer, which eventually shrinks the dimension to the number of categories that we want to be able to predict. So this is normal, right? In the end, we want to be outputting a vector of size, the number of categories that we can predict, right? And here, a very classical move. We use a softmax function. So softmax is just a way to make sure that what you output is somewhat a probability. So in the end, these vectors, the vectors that you output, their sum should be equal to 1. This is kind of a property that we'd like to make sure that the norm of the vector is meaningful. All right. And then once you've done this, you can just look at a summary of what we've done so far and make sure that we end up with what we just described. So our model has 3 layers. We can see the dimensions and how much hyperparameters this results to in the end. All right. So then once we've said this, we haven't yet defined what optimization problem we want to solve exactly. So in our case, what we want to maximize is what we call cross entropy. So in essence, this is just a metric to evaluate how close our vector is to the true y. I won't go into the details, but you could use other losses here. This is really canonical in our case. And at the same time, it'd be nice to track the accuracy of the model. So whatever metrics you want to be able to track, you should put in there. And this Adam optimizer is just the gradient descent strategy that we'll be using here. So we could use something maybe more intuitive, like a stochastic gradient descent, like vanilla stochastic gradient descent. But the Adam optimizer again is the go-to strategy in this sort of setups. All right. Lastly, what we do is eventually we train the model on the training data. What we do is we leave part of the data out of the training, just to Sorry,
I had one question. The number of nodes you selected for the first and second test layer.
Yes.
How do you get inspired with how do you select the number of nodes, for example, to be there?
Yes. So yeah. There's a question in the room. Someone's asking how you decide on what's a good strategy to choose the number of neurons at each in each layer. I think so. There's a huge literature about how to use, for instance, variational autoencoder. So in essence, when you know that your problem is your input is somewhat high dimensional or has a high number of features, but that you somewhat expect to be able to represent it in some much lower dimensional space, shrinking this down to any dimension that makes sense to you is a vanilla good strategy. And then as to why we have chosen these dimensions here, I won't pretend I know. It's just you got to start somewhere, and it runs fast. But then obviously at some point you want to somewhat cross-validate these hyperparameters. So, but in general, it's just a very classical approach to shrink everything with these orders of magnitude for such a classification problem. Yes.
What's the general rule of thumb that you use, particularly when it comes to with the sheet, how many knots that you put?
So another question in the room: what's a rule of thumb maybe for deciding on the shape? So you mean the number of layers, maybe? Yeah. So you'll see again, it's very empirical. One of the questions one of the exercises at the end of the notebook is to try and add layers and see how this improves or degrades accuracy. So you'll see that for such problems where you don't have that much training data, it's essentially useless to add more layers. So, I mean, here an empirical strategy for choosing the optimal number of layers is just to try until it breaks. But it's kind of I don't think there's a proper framework for inferring these things on top of your head, like without having insider's knowledge about your data. We'll leave 20% of the training data out for validation purposes. And then what we do is we will take samples from our training set in groups of 10 at a time. And so every sample will take the features, have them run through our model. This will yield a prediction, so a vector Y of predictions, and we'll compare it with the actual label of the data. All right, we'll do that for 10 samples in a row, and then we will optimize the coefficients of our model through backpropagation, so as to minimize our cross entropy loss on these 10 samples. On these 10 samples of the batch. And we will do this until we have seen every samples of our training set. Eventually, once we're done, this is one epoch, and we'll do this 10 times overall, right? So we'll see every sample of the training set 10 times overall, all right? And this is actually super fast. Like if we go, it just takes a few seconds to train our model. All right, so we've been collecting this metric, the accuracy, both on our training data, but also on the validation set. So we can plot it right away. So here's the loss. Actually, let's start with the loss first. So the loss is this cross entropy. It's just a metric between what we've predicted and what was the ground truth. We see that the loss decreases as the number of epochs grows. So it means the more training data we feed the model, the better the better it can fit this data. So we're actually learning something on the training set, but we're learning something that doesn't seem so generalized to the validation set. All right. Another way to look at it is to look at it from well, actually, this tells us something a bit different. But like we can look at the accuracy of our decoder. We see that we can reach almost like 100% accuracy on the training set, but this does not generalize to the validation set. And then we still have some left out data, so something that is not the training nor the validation data. And similarly to what we have seen before, we can use our model to predict. Yes, so this is actually the accuracy on so F1 score here for our training data, and we can see right away that it does not generalize to some of our left out data. All right, we can look at the same confusion matrix that we've been looking at in the previous example to see what classes seem to be correctly predicted and what classes are a bit tougher to grasp. But again, I think don't make it's tempting to make huge like great conclusions from these. Just recall that the number of samples we have for each class is fairly low, so it's not like we're doing things that are very statistically relevant here. All right, so that's just it for this bit of this part of the tutorial. There are a few questions. So the first one is, what's the most difficult category to decode? So the answer would be the same as in the previous tutorial. You can try and see what true labels are actually poorly predicted. So apparently it's hard to predict a bottle, and you really want to say house most of the time, in a fair amount of times. But again, this is like a bit fuzzy. Maybe it does not make that much sense. However, I think the second bullet point is more interesting. So we see in these curves that we tend to overfit the training data. Is there a way that we can try and make sure that our model is more robust to new samples, so unseen samples? And one very nice piece of work from 2014 involves adding what we call dropout layers in neural networks. So dropout layers, as surprising as it seems, just discard neurons altogether. So you set a probability of a neuron becoming 0 independently of what signal it had in the first place. So let's try this. We can simply import a dropout layer from Keras. We'll start a new model. We'll add our first dense layer, second dense layer, and then right here, can add a dropout layer. Let's say we'll set a probability of 0.5, which literally means we'll set a neuron's value to 0 50% of the time, right? So we discard information for like half of the outputs of this dense layer. All right, and I think that's just it. And then we add a dense layer. So the last layer is a bit different. It couldn't be dropped out, right? Because it's the one that projects our previous embedding to the space of categories. All right, and let's try again. So let's train this model. All right, and then let's remember the figures right here. So the best loss that we could achieve on the validation set was about 0.1 here, whereas the loss would go to almost 0 in this case. And in the new figure, we see that the loss for the validation set continues to go down. So this is way more interesting, actually, because like what we see here is different than what we had before. We see that if we were to add more epochs, it's very likely that the model would capture a bit more information, something that generalizes on the validation set as well. So it probably means we're going the right direction, right? And maybe adding some more epochs to the training phase would be better. Let's look at the accuracy. So same thing with the accuracy. We see that we no longer have this vanilla 100% accuracy. Now we do a bit more poorly on the training set. But however, on the validation set, we do a lot better. Like we gain almost, I think, 0.1 here. All right, and we can look at this directly in the performance. So this was the performance on the test set. Oh, and we do. Sorry. Actually, we do worse. So I start. Maybe 0.5 is just too much. Maybe we could try to be a bit less enthusiastic about dropping values here and use 0.2 or 0.3. I don't know. Let's try. All right, 0.2 doesn't seem to change much what we had before. Anyways. I'm running out of time. I just want to leave you with two ideas. So the idea of this specific bit of the workshop was to give you an idea of like what you can do with nonlinearities and like more complex decoding models. And we've been decoding classes, but I just wanted to take 2 minutes to tell you what other labs are trying to decode at the moment. And I just wanted to show you two very recent pieces of work. One from people in Singapore, Hong Kong, and Stanford. And what they're trying to do is, so they have the same kind of features that we have here. So activations in the brain through MRI imaging. And they're trying to reconstruct images that people are seeing, all right? So instead of doing a classification problem, this is like you can see this as a very difficult regression problem in the feature space of images. And so I'll just leave this for 1 more minute on screen if you want to take a picture of this and maybe like save this reference. But like, so the top row are the actual images that people are seeing, and the bottom row is what's generated by the model. And I'll just leave this 10 more seconds on screen for you to appreciate the mind-blowing resemblance between these pictures, I think. And for those of you with who are interested in this and with computational background, they're using diffusion models. And I think it's interesting because they actually use brain encoders. So what you would be taught upstairs if you were there. But basically, they're solving a problem which they consider is more easy to solve. So they're trying to predict brain activations given an image. And then they're using this encoder to guide their search into a space of images to try and find the images that best describe what's happening in the brain. Anyways, I don't want to go too much into the details, but this is I think fairly interesting. And for those of you who are interested in language, this is also something that people try very hard to decode at the moment. And there's this very recent piece of work. So yeah, this piece of work is 2 weeks old, right? It was published like literally almost a month ago. This one is from late September this year, and it's somewhat the same setup. People are trying to decode things using fMRI features. It's just in this case, what they're trying to decode is language in a broader sense. So people in the MRI machine would be hearing stories. You get the MRI images of these people in the MRI machine, and you try and decode back what these people were hearing. All right, and again, so I think the metrics in this piece of work are a bit hard to grasp. So it might not be as accessible as the other paper that I showed you, but still, if you're interested in decoding, I think a lot of things are moving at the moment, and that these two articles should give you some ideas what's coming next. Thanks a lot for your attention. I think it's time for me to leave the floor to Shireen for some knowledge about graph neural networks.
Being familiar with LAS2 model, we started actually with SVM, which is a classical decoding model. After that, we have ANN, a vanilla ANN, which is MLP. And right now, we are going to getting familiar with a sophisticated model. This model is called GCN, is Graph-Neural Network. And the main idea of that is that this model combines graph theory with convolutional neural network. Here we have a schematic view of the pipeline. Like other decoder, the input are all bold time series. We will map those time series on a predefined brain atlas or like region of interest. After that, the output would be two-dimensional time series matrices. And we are going to make a brain graph using those time series. Actually, in brain graph, each node is assigned to each region of brain, or we can say parcel. And the age will be, like we can decide about the sparsity of the graph. In this tutorial, we use 8 connection, and it's going to choose the 8 strongest connection based on the functional correlation of the brain region. So it was what I explained was the first row, and the second row shows the model, the decoding model. We have a time series and a brain graph, and we use them as an input of our the stack of convolutional layer that we have. In this tutorial, we have 3 layers. It's actually a hyperparameter that we should tune depending our input data. But here we chose 3 because it seems that the decoding result was fine, and we were caring about the time also. Each convolutional layer has 32 graph filter. After those convolutional layer, we have a layer of average pooling, which is going to give a average of our each of our feature map. And after that, we have exactly same MLP model that Alexis presented previously. And the result, the prediction result, came after all those stack of the different layer of models. Similar to previous approaches, I just run these cells to have the data, but we are loading the data, and the shape of the data is obviously the same. So I didn't run previous cell. You can see that we have 4,100 time point or time series, and we have 675 brain region. So, and here is a graph construction. I told you the general idea of the graph construction, but if you are curious to know more detail, I put the link to it. Look better in the Jupyter book, but even here is the link to the tutorial from 3 years ago, which Dr. Zhang, who developed this model, had a tutorial, just one session, about how we can construct a graph. So you have access to a slide, and you have access to GitHub repo, and you have access to Binder, so you can try and see how those graph construction works. Okay, as I told before, what we care here for graph is a correlation that we have between different regions. So for measuring the correlation, we are using Neuland connectome connectivity measure with correlation basic. We can choose different things, but here we are caring about functional correlation. It can be like gray matter density or some other strategy. So here we take the correlation, and you can see, because we have 675 regions, this matrix is not very clear, but what you can see is the main diagonal shows the correlation of each region with itself. That obviously is the bold thing, that each region has the most correlation with itself. And now is the time to generate the graph based on the correlation that we extracted previously. And just here, we call the graph construction a script that I talked about. If you want to see and try it with detail, you can check the tutorial that I put the link to it. And you can also check the script, which is in the source folder, and the name of that is graph construction. So we define here the number of the edges, number of connection that we want to have for each edges. We chose 8, which is another hyperparameter that you can tune it based on your input data. And obviously the matrix is symmetric because it's not direction. And we don't have self loop. I mean, there is no loop for each region. So and now is the time. So far, we have the graph, and we extracted the time series. So both input for our model, for our decoding model, are ready. So we are going to prepare the dataset for brain decoding. Here, just because the categories are scattered, I concatenated all the categories which are the same thing, because the model gives us the opportunity to choose the window size that we want to sampling based on that. Here, I use just single time point, which means just single volume, which is a little bit challenging for when we have a big data. But here, because the data set is toy data and it's not that big, we prefer to have a smaller time point to have more sample for training the model. And here is a script about the window time that I talked about. We are going to split all the concatenated data to the desired window length, and all of them will be saved, like the label file and also the time series will be saved accordingly, like in a directory that you will see under the data folder. Okay, and now is the time to a splitting data set. As you saw in previous approaches, they used 20% for test and 80% for training. Here we have also validation. We need to define validation here. It's not automatically inside the model, so we put it aside. In other model, there is cross-validation inside the model. Here we should define how much of percentages of data we want to consider for validation. So we use time windows dataset for splitting the dataset, and after running that, you see that here we have training a split, validation a split, and test a split according to the percentage that we use, which is 20% for training, 10% for validation, and 70% for test. So the data is ready as well, but we need to run data loader because at the end of each epoch, we need to shuffle. We don't do it, actually, model automatically shuffle it, and we need data loader to make sure that it's not going to mess up with the data and everything are fit and like shuffling doesn't cause any problem. So and now we are going to start the data is ready, the graph were ready. After that, we generated the data, and now we are going to start a decoding model. As you saw in a pipeline that we had at the beginning, we have 3 Graph-Convolutional layer, 32 filter at each layer, global average pooling to each convolutional layer, similar to what you saw in the previous presentation, has ReLU activation inside. And after 2 fully connected layer, we also have softmax. And normally that's what we use like for the output layer. Generally speaking, we use softmax, and for the hidden layer, ReLU most of the time is used. So it's pretty standard things. And we are going to run the model. Here is our model. We gave all the parameter. We defined the number of time point, our byte size, also like the number of classes that we have, which is the length of the category, which were 9. We had 3 images category plus regressing state that we didn't regress out, so we have 9 different categories to decode. And now is the time for training and evaluating the model. So as you saw previously, also here we have different epoch, and we have Adam as optimizer, which obviously can be changed. It's another hyperparameter, and for loss function, we use cross entropy loss. We can also choose other like a strategy, but this one seems pretty standard one to use. And here we are going to run the model for 25 epoch. And at the end of each epoch, you can see the average accuracy per for validation. What you see here is it's not training, it's validation result. And you can see that the result will improve because it's in neural network, we have back propagation. It means that the loss function and the weight will be normalized and optimized by learning. And when model learn and optimize the loss function for the next epoch. So the model training got better and better by the time. Obviously, we can change the epoch, but we should choose something. It doesn't mean that having more epoch at the end of the day with adding to the epoch, we will have the better result. It depends really to the size of the data. And do you have any question about that? Because it's going to take a little bit. No question?
I have a question.
Yeah.
The edges in the Graph-Convolutional network that you created, where did the kind of edges decided on which kind of nodes to place the edges?
Okay, we have a question in the room about how the edge will be defined. We don't define it manually. We just choose the number of connection to each edges, and all the edges. I mean, here we had 675 region, and all of them are the number of we have all of them. All of them are the edge. All of them are one node. We have in the graph we have 675 nodes, and each edge is connected to 8 other edge with the highest connectivity. So we don't define anything there. All of the region of interest has the edge, but the connection will be based on the strength of the connectivity of them.
Where does the strength of the connectivity come from?
We have another question about how we can define the strength of connectivity. The strength of connectivity come here from the functional correlation. We can have different, it can come also from a structural measure, like the density of gray matter. But here, what we care about was the functional correlation. So that defined the connectivity. So just one thing that you can see the result of the this model, despite it's way more complicated comparing to previous model, is not higher than what you saw previously, because this complicated deep learning model shows their advantages when we are dealing with high dimensional data and huge data set. So it's not something that can show the better result here. For example, convolutional layer is the best approach so far for overcoming curse of dimensionality. But here we are not facing curse of the dimensionality, and we don't have huge data set for training the best this kind of model. So the average accuracy is not that high. Of course, we can optimize it, but it's not great. But when you have let's say the data set like HCP, I don't know if you are familiar, if it's a data set consisted of 1,200 participants, so it's a huge data set. And Dr. Zhang, which used that data set, reached 95% accuracy for decoding 21 tasks at the same time, so which is great. And for sure, the other model like SVM can't do that, or MLP is not able to do such a decoding. So anyone picked that I didn't do one of the procedure that we have here. I went through everything, but one of them wasn't necessary here. I didn't apply the bold time series. I didn't map it to the brain atlas because the dataset came with 675 regions. So it wasn't necessary, but it's necessary when we are dealing with voxel level data, which this dataset is an old dataset, but like newer version of dataset are at voxel level, and we have thousands of like the second parameter when we took a shape of the X, our X data is thousands of voxels. So for sure, we need to map it on a predefined brain atlas, or even Nylearn have some a strategy like dictionary learning for extracting brain region using data. So that's why I put it as an exercise to try. We can do it with this data as well, but it decreased the accuracy because when I tried that, I ended up with like 60 region of interest, which is not good when we are looking for 8 connectivity. If you wanted to try that with like bigger data, actual new year data, for sure you need to apply the brain parcellation there. And so we can, for the exercise, we can also try different time windows. I don't think we have time, but it's pretty easy. Like when we define the time windows, instead of 1 window length, we can put 2. So for each sample, we have 2 volume, and we can see how the result will change. The next exercise was trying different loss function. As I addressed, like the best, we can try all the like model that we use, all the strategy that we use. We can try different other parameters which are available and find the best parameter that fit our data. And another thing that we suppose, if you are interested to do, is to try to change the parameter and put those in an actual code instead of like manually change it. So try to define it in a model that like by one nested loop, we can find the best fitting model and try to find the best parameter. And the last one is what I already asked you at the beginning of the exercise, that if we can try this model on the dataset with the voxel level volume, for sure we need to extract region of interest from data itself, or using the brain predefined parcellation. So that's another thing that I asked you. If you are interested, do it. And
of our session here, maybe once more, excluding myself here right now, give it up for all the instructors for a great content and stuff. Yeah, so once more,